I'm part of the group Charging a Car and Charging the Grid. My name is Jason Worthen. I'm working with Dustin Hughes, Blake Wayment, and Joseph Nielsen. And our faculty advisor is Dr. John A. Palmer. So for my portion of our project, my focus is working on the car side power electronics. However, because of the similarities between the car side power electronics and the grid side power electronics, Blake and I have been working together to get these things to work. So to start off for this milestone, we decided that we were going to go back to do the switching rectification as opposed to using the diode rectifier. We were able to get this working by placing a diode there on the DC bus, as well as using the inductor and capacitor there as shown. The reason we made this decision is because it does allow for more control of the output voltage, and we were able to get this working correctly. So it eliminates the need of extra diodes that wouldn't be used for the inverting circuit. That additional diode is something that would have to be switched out and removed from the circuit when we decided we wanted to operate the circuit in inverting mode. So here we can see that we get out a pretty good voltage, about 100 volts output here, or close to it, 95 volts. And with that, it's kind of low. We might end up having to add a boost converter in order to get up to where we want it to be. But as far as right now, it's a reasonable output. Part of the reason we have that problem is because we need to limit the current, which is shown here in blue. We don't want that to go too high and trip the breaker. Here we're getting an RMS current around 16 or 17 amps, so it should be we should be under that the threshold for tripping a standard 20 amp breaker. So we did all our simulating in the previous milestone, and Blake will discuss some additional issues with simulation that we came along as we were trying to do that, and trying to finalize things for the second milestone, and some reasons is why we weren't really able to take that any farther. So we decided to go ahead and start prototyping. We purchased our IGBTs. As well as our gate drivers. So here we decided initially we were just going to test these components one by one and then put them all together. So initially we decided we were testing the IGBTs shown here, and then we have that in series with a resistor, and we just applied a low power 15 volts to test it. And then by doing an input voltage there of about 5 volts, we were able to turn it on and off. We used a square wave to simulate that, and then we could measure the voltage from the collector to the emitter and see that the transistor was being switched on and off. And here we have a video showing that test. So here we can see the IGBT that we have hooked up. The gate is on the left, collector in the middle, and emitter on the right. We have that connected to our resistor, and we have a 5 volt peak-to-peak sine wave controlling the gate, and 15 volts across the IGBT, and you could see the 60 hertz output there at that point. So then we also decided we wanted to test the gate drivers. In order to test the gate drivers and be able to use them to prototype, we used an 8-pin SOIC to DIP adapter. And we were able to, they're just little surface mount chips. We were able to solder it on there and solder on some headers in order to use them on a breadboard. We tested the low side gate driver. We have both a low side and a high side gate driver on these chips. The low side is the simpler to use of the two. The only difference between the low side and the high side is where the resistor and the load is placed in relation to the IGBT. For the low side test, the emitter of the IGBT is connected to ground, and the resistor connected to the collector. For the high side test, the IGBT is connected to the power source on the collector side and to the resistor on the emitter side. And then we were able to use some bootstrap capacitors, and that is what is able to provide the burst of charge needed to fire the gates here. Initially, we struggled getting the high side to work, but we were able to find the right values of capacitors, and we were able to get that working. So here is first we have a video here of the low side test, gate driver test. We'll play that. There we can see the gate driver on the adapter board hooked up to the breadboard. We have a 20 volt peak-to-peak supply operating at 60 hertz, and then we have a 60 hertz output across the collector to emitter voltage there at the end. And then here is the video for the high side. There you can see our chip with the capacitors and the diode and all the connections necessary for the high side gate driver. We have a 60 hertz 20 volt peak input signal, and there you can see we're getting a clean sine wave for our 60 hertz, it's a clean square wave, excuse me, at 60 hertz for the output of the high side gate driver. So the next step was to try to use the Arduino in order to operate the gate driver. So we used the library called Timer1, and we were able to use that to create a PWM signal on a couple of the output pins on an Arduino, with the ability to be able to modulate the duty cycle on those pins. So initially we just we hooked up to those pins. We used those as the input to the gate driver for both the high side and the low side, and then we were able to get a high side and a low side output from the gate driver. We didn't include more videos of that just because it's be a lot more of looking at the same old 60 hertz square wave. So then we decided so at that point when we got that working, we then hooked up two separate circuits, one for the high side IGBT and one for the low side, and we ran them using the Arduino hooked into the gate driver, and then hooked into those the same circuits that we used to test the IGBTs, and we were able to see the 60 hertz square wave looking at the collector to emitter voltage on both the high side and the low side, so we were able to effectively operate those. So part of this, in getting a rectifier to work, using these switching components, we need to be able to read the sine wave that we're going to rectify and be able to determine if it is in the positive half of that sine wave or the negative half of the sine wave, because that's going to determine which IGBTs we're going to be turning on and off. So we determined that we would use the Arduino because it has the ability to read an analog signal between 0 and 5 volts. And so for an initial low power test, we used a 20 volt peak-to-peak sine wave just from a signal generator that we were going to try to rectify. So in order to get that 60 hertz sine wave being a 20 volt peak-to-peak signal into that 0 to 5 volt range, we created the following circuit. Here we have a 5 volt supply, and then we have our input voltage of plus 10 and minus 10 volts there, VN, and then we have the resistors R1, R2, and R3. These resistor values are calculated. We chose one, and we chose R2, I believe, to be a 100K, and then by setting the node there at between R2, R1, and R3 to be equal to 5 volts when VN is equal to plus 10, and we set it to 0 when VN is equal to negative 10, and then we were able to determine the other two resistors that would give us those values, R1 and R3. And this gave us a sine wave with a 2.5 volt DC offset that was a 5 volt peak to peak. So we achieved that 5 volts, 0 to 5 volt range there. And then using coding in the Arduino, we were able to then manipulate it further to decide whether that sine wave was in the positive half or negative half. However, the problem with the analog read is that it was too slow. So we needed to do something to create some sort of a digital signal in order to get this to work properly. So in order to create this digital signal, we took that same output from the resistor circuit on the previous page and we put it into a comparator. That's what you see there hooked up to the non-inverting input of our op-amp there. And then we used the resistors R1 and R2 and a 5 volt source to create a 2.5 volt reference point there on the negative voltage. With R1 eventually is going to be a potentiometer so that we could dial it in exactly where we need it to be. and we can basically get a high output, a 5-volt output when we are in the positive half or above 2.5 volts, or a 0 when we are on the negative half. And then that provides us with a digital signal that we can send to the Arduino, and then that will tell us whether the sine wave is positive or negative, and be able to read a lot faster. However, we still ran into some speed and some timing issues. We could potentially get a rectifier working at a 60 hertz signal. We still ran into some timing problems and getting it to read at a consistent rate so that we could get an accurate representation of the 60 hertz signal. That's something that could probably be solved. However, when we looked at the 20 kilohertz, we were unable to read the data fast enough in order to have a rectifier that would operate on the Arduino at 20 kilohertz. We would see where we were skipping entire cycles or the entire positive half of a sine wave on our data, and we were unable to figure out a way to make this work faster. We looked at a couple different options and nothing seemed to work. So we're probably at this point going to see if we can look at using the Raspberry Pi. It seems like it can do a better job. Anyways, thank you for your time, and this was the work that I accomplished in the second milestone for our project. Thank you.